recording. And screen. Okay. Perfect. Okay, very cool. Let me just open up a new doc and then we'll get started here. Oh, nice. Okay, good that we're starting late then. How did the project go for you guys? Yeah. Alrighty. So there's a worksheet over here if no one got it. Did you get one? Or... No. Okay. Yes, yeah. Alrighty, very cool. Okay, so yeah, today we're going to talk a lot about kinematic constraints. So let me just set out our agenda, and then we can actually get talking about what we're going to do. All right, wonderful. Yeah, so we're going to start out about talking about Pfaffian constraints. So Pfaffian constraints. Then after we talk about that, we're going to talk about something called an equivalent control system. Control system. Yeah, that looks okay. And then finally, we're going to finish things up by talking about Lie brackets. Okay. So today we're mainly going to focus just on like conceptual stuff. So there are a couple problems on the discussion worksheet. We're going to do them if we have time, but I think, yeah, in my opinion, this is the trickiest topic that we cover in this class. So I think it's, yeah, it might be a little bit more beneficial to do some more conceptual ideas. What do you guys think about that? Like, how have you been feeling about the lecture stuff for this so far? Yay or nay? Okay. All right, very cool. Okay, so with that, we can get started by talking about Pfaffian constraints. Okay, so just as a quick show of hands, how many of you guys took 106A? Just okay, very cool. So in 106A, right, I'm gonna take us a little bit back to last semester. What we did is we talked about 106A. We talked about Lagrangian dynamics, right? Lagrangian dynamics. And what we said is we had these things called like generalized coordinates, right? So we had generalized coordinates. Maybe they were called like Q1, Q2, Qn. We had n of these coordinates and they represented like n different positions in our system, right? So if I had like a pendulum that was swinging around, I would maybe pick like theta to be my generalized coordinate. Or if I had a turtle bot that was moving, maybe x, y, and then the orientation angle, right? Things like that. So once we had all those generalized coordinates, what we said is we could apply Lagrange's equations. So it's the ddt, dl, dqi dot, minus dl, dqi is equal to fi, right? So we had these equations, and these went ahead and generated these nice, like second order differential equations, okay? So that would tell us what Q1 double dot was, Q2 double dot, all the way through Qn double dot, okay? So that was really great, right? It gave us a lot of information about how our system is moving. But in a lot of these systems, right, especially in robotics, right, when we look at things like a robot arm or a turtle bot when it's moving around, it turns out that there is a simpler representation. So simpler representation of our kinematics. Okay, so not necessarily about like how forces are interacting with systems, but how like different quantities like velocities and positions and that sort of thing interact. So what today we're going to do is we're going to talk about like these simpler representations. They're called like kinematic constraints, and we're going to see how we can use them to our benefit in designing very nice controllers and path planners for different systems. Okay. All right. So we're going to start off by talking about a turtle bot. Favorite example. So I'm going to just sketch out this little turtle bot over here. Those are its wheels, and maybe it's following like this path over here. Okay. So let's try and think about what constraints are on the motion of the turtlebot. Do we have any ideas? Like, what are some constraints that exist when this thing is like moving around in the plane? So like that's x, y, then its angle of orientation is given by like some angle theta. What do we think? Yeah, like constraints on x, y, or the velocities or anything like that. Do you have any ideas? Sure, yeah. So we could have like constraint. Yeah, sure. X dot, y dot, theta dot. Right. It can only move so fast, right? All right. Yeah. Sure. Yeah. So that's good as well. So it turns out that there's something that is like a little bit more fundamental to our turtlebot's motion over here. Okay. And what this is that we have a constraint that the turtlebot, it can't really slide side to side like that, right? If it could, that would be great. You know, that would make our lives a lot easier. But our turtlebot can actually only travel like in the direction of its heading, right? So what we say is turtlebot can only travel in the forward, backward direction. Okay, so not side to side. So this is a really important type of constraint, and it has a very special name. Sounds kind of fancy. It's called a holonomic, or excuse me, non-holonomic constraint. Okay, so we're going to talk a little bit about what that means, in more detail a little bit later on. But for now, what we're going to try and do is, we have these three different constraints over here that we've thought about for our system. Now, maybe if we're trying to like go ahead and develop some controllers or path planners around these, it'd be kind of nice to have some conventions. Okay. So we're going to develop a conventional way of writing a constraint called a Pfaffian constraint. So Pfaffian constraint, you could think of it like a convention for writing constraints on motion. Okay. So what I'm going to say is, let's imagine that I have like some generalized coordinates, q1, q2, all the way through qn. And those all have like derivatives, right? Like we could take like q1 dot all the way through qn dot. Now, a Pfaffian constraint on the motion of this system is something of the form omega I of q times q dot equals 0, okay? So this thing, omega I over here, it's a function of our state. So function of generalized coordinates, q. And what we're saying is that it imposes this relationship on, the different velocities that we're having, okay? So it poses a constraint on the velocities of our generalized coordinates. All right. So when we set up this omega I of q equals 0, what we're doing is we're essentially taking a dot product between this omega I and this q. But by convention, we usually just take omega I to be a row vector. Okay. So it's like we have omega I1 of q all the way through this omega I n of q. And we're multiplying that by, q1 dot all the way through qn dot. And we're saying that that's equal to 0, like a scalar 0. Okay. So overall, what this does is, it's saying, all right, we have this constraint on these linear combinations of the different velocities that are in our system. Okay. So it turns out that for robotics, we could really represent anything we want in this form. All right. So for everything we could describe with Lagrangian dynamics, we could always write the constraints on the velocities of the system in something that looks like that. Okay. So what we say is that for a trajectory, q of t, to satisfy the constraint, right, we must have to satisfy this equality over here. So omega I of q times q dot of t equals 0 must hold for all time. Okay. So all that we're doing is we're saying, all right, we have, these different constraints that are going to scale up our different velocities terms. And when we add all of those up together, we should get 0 back out. All right. So do we have any questions about this like general form of what a Pfaffian constraint is? What do we think so far? Good. Yeah. So it's always going to be equal to 0 in this case, because for dynamics, what we like to do is we say, like, if we're traveling in 3D space, like something like that, it's not necessarily like Euclidean space, but what this constraint is essentially doing is it's restricting our motion to some sort of like little surface in here in space. So you can imagine, like, instead of traveling along like any surface out there and just moving freely, it's actually just constraining us to this little surface over here. And we could represent a surface in any dimensions with something times this equals 0. Yeah, that's a great point. Okay. Yeah, any other questions? How are we doing? Okay. Oh, yeah, what's up?
Is that just like are you doing some sort of approximation thing, or is it just like?
Yeah, so not quite. So essentially, like, if you imagine that you have like a pendulum over here that's swinging around, we know that the tip of this pendulum will always be along like this circle over here. Okay, so that circle traces out a little surface in space. Yeah. All right, very cool. All right, so a Pfaffian constraint, right? Omega I of q times q dot equals 0. This directly constrains our velocities in our system. Okay. And now a really important question that we want to ask here is, does it directly constrain our positions? Does it directly constrain our positions? Right? And it might seem like it does at first, right? But it turns out this is actually kind of a little bit of a subtle question over here, right? So if we have this constraint that says omega I of q times q dot equals 0, does that actually directly enforce, like, if I can travel over there or over there? What do we think? Yeah. Thoughts? I know it's a Friday. Yeah.
I just think that, like, if WI is dependent on Q,
Mhm.
then maybe somehow, like, when you expand it, there's some limitation.
Okay. Yeah, so it could directly impact what Q we can reach. But it turns out that this is not always the case, all right? So not always true. So just to think about why this is, let's go ahead and think about our turtlebot example over here, right? So we had this turtlebot and we said we had this constraint number 3 over here, right? It can't slide side to side. But from experience, right, when we're using these turtlebots in lab, even though it has this constraint on its kinematics, we can still more or less drive it to any position we want in space, right? So what this tells us is that not all Pfaffian constraints directly constrain position, okay? So not all Pfaffian constraints directly constrain position. But it turns out some of them do, right? So if we just go ahead and we look back to this example of this pendulum over here, right? We know the position of this pendulum has to be somewhere along this arc, right? So the pendulum position is being directly constrained, right? Like the XY coordinates of this. But our turtlebot position isn't being directly constrained, okay? So we sort of have these two separate types of constraints, one that's directly constraining our position and one that's only constraining our velocities, okay? So what we want to do now is we want to try and classify these constraints. All right, so before we do that, do we have any questions about the distinction between these two types, like why this is showed up? What do we think? Yep. Okay, cool. All right, so we were just talking about this type of constraint that, maybe directly constrains your position, all right? So we say that a constraint called omega I of q, q dot equals 0, is said to be integrable if it is equivalent to some h of q equals 0, okay? So what we're saying is if omega I of q times q dot equals 0 can actually be equivalently represented as this function h of q equals 0, right? Where this h of q just depends on positions. Then it's said to be an integrable constraint, okay? So these integrable constraints, they directly constrain our positions. Constrain our positions. All right. So an example of that would be something like the pendulum, right? We know as it's swinging along, x, y is entirely determined by theta, right? So we could really determine that with one of these constraints that's purely on our position over here. Okay. So if you wanted to get back from h of q to this omega I of q times q dot form, you could just take the derivative of this thing in time and apply chain rule, and that's going to come right up. Okay. All right. Okay, perfect. So what we have so far is we have these normal Pfaffian constraints, right? And maybe we want to determine if they're integrable, right? If they're equivalent to a constraint that's purely on our position. Okay. So what else? Well, what happens now when we have a system of constraints? Okay, so now instead of just thinking about one constraint, omega I, I'm going to say that imagine we have k constraints. And I'm going to call them omega 1 of q, q dot equals 0, all the way through omega k, q, yeah, q dot equals 0. Okay, so what if we want to talk about like whether all of these constraints are integrable or only some of them are integrable? Turns out there's some really nice and like fancy sounding language we could use to discuss this idea. Okay, so if all k constraints are integrable, right? So remember that just means that each omega I of q times q dot equals 0 is just equivalent to a pure like algebraic constraint on our positions, right? Then we say the set of constraints is something called holonomic. All right. So this is a Greek word that means something to the effect of integrable, which is why it ends up being used in this case. All right. So that's a holonomic system, right? If we have all of these constraints and all of those constraints are entirely equivalent to just a pure constraint on position, we say our whole set of constraints is going to be holonomic. Okay. So if no constraint, on the other hand, is integrable, right? None of those are equivalent to algebraic constraints. All of them are like just purely velocity constraints. We say the set of constraints is, in this case, non-holonomic. All right. So what else, right? We have these two extremes at the moment. Now we could sort of look at somewhere in the middle, okay? So if some constraints are integrable, we say the system of constraints is, in this case, partially non-holonomic. All right. So these three constraints tell us about, how our system is going to be moving around, right? So if we have holonomic, we know our positions are constrained. And if we have non-holonomic, only velocities are constrained. Okay. So this is going to be some terminology that we're going to use a little bit going ahead. All right. So how do we feel about this so far? Do we have any questions about this idea of like holonomic versus non-holonomic, integrable, like what any of these terms mean? How are we doing?
I guess for complete non-holonomic,
Yeah.
Why is it only velocities? I guess position cannot be constrained at all to that.
Yeah, so your position won't be directly constrained. So sometimes it works out that even if you have a non-holonomic constraint, you won't be able to reach some states in finite time. But in general, it'll be that like, okay, if I see any state around me, I'll be able to get there given like sufficient like infinite time. Yeah. So it's just sort of constraining like the directions in which we can move more than the actual positions we can move to. Yeah. So yeah. So it constrains our direction, but not our position. Okay, yeah, great question. Any other questions? There we go. All right, wonderful. Okay, so let's go ahead and actually, yeah, I think we're doing well on time. So we could try a quick example real quick. All right. So example. So what we have over here is we have a pendulum. Right. So pendulum is sort of swinging around at an angle theta over here. And its center of mass is located at x comma y. And we have this distance like L to the pivot point over here. All right. So what you can try and do in this case is try and write the constraint on x comma y in terms of theta. Okay. So I'll give you guys just a minute to do this. All right. You could try and work it out with a little bit of trig if you can. Now, just to make this a little bit easier, I'll define x to be the variable going down here and y to be going across over here. Okay. So if you want to give this a try, we'll regroup in yeah, just about a minute, and then we'll sort of discuss some of the pieces. Okay. Okay, so do we have any ideas about how we might write some of the constraints on this system? What do we think? Any volunteers? Yeah.
We would start with the trick of like x equals L cos theta, y equals L sin.
Sure, yeah. Yeah, so that's actually perfect for the system, right? So it turns out that if we just subtract like L cosine theta to one side, right? We have x minus L times cosine theta equals 0, right? That could give us our first constraint, right? Which is like h1 of q is equal to 0. So that's a purely algebraic constraint on our system dynamics over here, okay? Now, similarly, we could do that for the second one, right? So we could do y minus L times sine theta equals 0. And that gives us our h2 of q equals 0, all right? So what this tells us is that these two constraints are going to be integrable, right? And if both constraints are integrable, then the system of constraints is said to be holonomic. All right. So just as a quick note, when you're writing out these constraints, they're not always going to look like they are in the Pfaffian form, like all the time. So for example, here, when we found the constraints, we found it was just easiest to write them as an algebraic constraint first. If you wanted to get those in like a standard Pfaffian form, you could take their time derivative, and then that form will sort of drop right out of there, okay? So do we have any questions about like how we did this process over here? Like, why is this a holonomic constraint? Do you have any questions? Yeah.
So if we were to represent and like we take the derivative of that, then we just bring those two.
So yeah, that's a really great question, actually. So when you're trying to write out the Pfaffian constraint, like what is Q? So when you're trying to figure out what Q is, you could actually start by looking at the unconstrained system, okay? So you look at the unconstrained system. All right, so in this case, we don't have the constraint that we have like a little pivot up there, right? So here we just have like an x comma y, and then we know that this sort of bar will have like some angle like theta, like we could just draw it there or any other place with respect to the environment, okay? So it's like we're starting out with 3 generalized coordinates in this unconstrained case. So we could say like q equals like x, y, theta over here. And then when we write the constraint, it'll be in terms of this. Yeah, yeah, great question. Yeah, so that actually brings up a kind of nice point over here. So if we were just to try and like derive Lagrangian dynamics, just like thinking about what we've been doing so far, like what generalized coordinate would we pick? It would just be theta, right? So we only need theta. as a generalized coordinate, okay? But if we think about this unconstrained case, right, we need 3 generalized coordinates. So what we said is that, we had our unconstrained number of generalized coordinates. We applied 2 constraints to it, and then we just ended up with 1 generalized coordinate that we needed afterwards, okay? So the number of GCs we need is equal to the number of unconstrained GCs minus the number of holonomic constraints, okay? So these holonomic constraints actually reduce the number of generalized coordinates we need to describe a system. So holonomic constraints reduce number of generalized coordinates. All right, yeah, any other questions? How are we doing? Yeah, what's up? So non-holonomic constraints won't actually reduce the number of generalized coordinates. Yeah, so this is going to be something that you guys prove on your own. Yeah, I don't want to give too many spoilers just yet. Yeah, what's up?
Constraint, I think, like if you have it, theta can only be minus pi over 2, pi over 2.
Yeah, so those aren't really considered like holonomic constraints that we could deal with in dynamics. Because if we just have our constraints, that's like, our system is going around like this, like we don't actually include those contact dynamics when we're writing out our Lagrangian dynamics formulas. So yeah, that would actually be something that shows up as a constraint force instead when you hit the walls over there. So that works a little bit differently to these ones. So these ones are purely on like, yeah, on your dynamics, like what velocities you can have and that sort of thing. Yeah. All right. Any other questions? All right. Yeah, what's up?
Could you essentially explain how holonomic constraints reduce the number of general coordinates?
Yeah, sure. Right. So in this case, right, what we had is we had like x minus L times cosine of theta equals 0, and y minus L times sine theta equals 0. Okay. So if we were just to consider the unconstrained case for this system, right, where we have q equals x, y, and theta, right? This says that we need 3 equations of motion to describe what this pendulum is doing, okay? So 3 equations of motion. But from these constraints over here, right, we know we could just solve for x and y in terms of theta, okay? So that means that 2 of these constraints, or 2 of these equations of motion, will actually be redundant, right? Because once we have that equation for theta, right, we'll actually be able to solve for x and y directly. So we don't need those other 2 generalized coordinates. Does that make sense?
Yeah.
Cool. Sure, yeah. All right. So let's talk about equivalent control systems, and then we'll move on to Lie brackets a little bit after that. Control systems. Okay. So far, right, we said that, all right, we have the system omega 1 of q dot equals 0, all the way through omega k of q dot equals 0. So let's say we had like k independent constraints, right? We could think of it like each one of these is doing something different to our dynamics, all right? No 2 of them are equivalent. Okay, so what I'm going to do now is I'm going to try and rewrite this in a matrix form, and then we'll see if anything nice sort of pops out of that, okay? So we'll rewrite our system, bless you, system of constraints in matrix form. All right, so let's say I want to try and rewrite it as a of q times q dot equals 0. What would I do? So what would my first row be over here? You have any ideas? What could I put in my first row? So I'm just going to go ahead and put in omega 1 of q, all right? Because just remember that these are row vectors, all right? So they're going across like that. Our second row, we could do omega 2 of q. And our third row, or excuse me, our kth row, omega k of q. All right? And these are all just equal to zeros over here, all right? So this is another way of writing our system of constraints. We've just sort of reorganized it into this nice matrix form, all right? So if, oh, scroll up. Oh, yeah, thanks so much. Yeah, good catch. Okay, so if q dot satisfies the constraint, what do we know about it? Okay, So I'm going to try and rephrase this question here a little bit, okay? So if Q dot satisfies our constraint, like what in linear algebra terms can we say about it and its relationship to this matrix A of Q? What do we think? Like, is there anything in linear algebra that, sort of reminds you of this form over here? Hmm? Yeah, right. So Q dot must be in the null space. Must be in the null space of this matrix A of Q. Okay? Yeah. Yeah, so in general, we just treat each of them as row vectors, and then we just say that, each row vector is a separate constraint. So you could have them like all as a big matrix, but then each row would be considered like a separate constraint under dynamics. Yeah. Yeah, great point. Okay, so what we're saying is that all of our allowable Q dots for our system, they must be in the null space of this matrix A of Q, okay? So now, if we think that we have, Q and Rn, right, when it's unconstrained, it's free to move around in, n different directions, and we have K independent constraints, this means that we're going to have n minus K, which I'm just going to call some new variable n. We're going to have n minus K equals m vectors, or excuse me, our dimensional null space. Okay, so what we're going to do now is we're going to try and find a basis for that null space. All right, so if we have an m-dimensional null space, right, an m-dimensional set of allowable Q dots, then we're going to have a basis of the form like G1 of Q all the way through Gm of Q. All right, so this basis is going to span our null space over here. And each of these are just a function of Q because our matrix A of Q is a function of Q itself, right? So if our matrix is changing, well, maybe the basis vectors for that null space are going to change as well, okay? All right. So what does this tell us about, all linear combinations, G1 through Gn, okay? So if I take, for example, U1 times G1 of Q plus all the way through Um times Gm of Q, right, where each ui is just like a scalar in R. What does that tell us about this entire linear combination over here? Is this going to be an allowable trajectory? Like, is this an allowable value for Q dot? What do we think? Yeah, right. So any linear combination of these elements in the null space is going to give us another element in the null space, okay? So every linear combination of this form will be like a valid value for like what Q dot is, okay? So we can say that, just using this constraint, right, and using all of these vectors that are in the null space of our constraint, we can actually form this equivalent control system, all right? So equivalent control system, all right? So now we're not only going to think about these U1 through UMs as, just simple scalars out there. These are actually like control inputs to our system that we could use to control where our Q dot is going, right? So by adjusting what U1 through UM are, right, we can get out a different Q dot because our Q dot must satisfy this constraint at all points in time, okay? So what we've done is we've taken our original Lagrangian dynamic system, right, which had those fancy second order dynamics, and we've gone ahead and we've just boiled it down to what that constraint is doing, okay? And that gives us this nice and easy representation just using this equivalent control system here of what our system is able to do, okay? So do we have any questions about this general equivalent control system form? How are we feeling, guys? Good. All right, very cool. Okay, so yeah, we'll come back to the practice problem a little bit later if we have time. For now, we'll just spend a little bit of time talking about our next topic, which is going to be Lie brackets. Fancy. So, oh yeah, what's up?
What does it mean for trajectory to be allowable?
Yeah, so a trajectory is allowable if it satisfies our constraint, right? So if we have like some trajectory of Q of t, right? It must satisfy omega I of Q times Q dot equals 0 for all time. Okay, just because that's our kinematic constraint that we're placing on our system. So if it follows through with our constraint, then we know it's something our system will be able to follow. Does that make sense?
Yeah.
Yeah. Yeah, what's up?
Why does it matter that constraints are non-holonomic?
Yeah, so we're going to talk about why that is in just a moment, actually. So this is actually something that does hold for the holonomic case as well. But when these constraints are non-holonomic, we'll actually be able to execute different plans using this sort of structure over here that we have. Yeah, it's a great question. Yeah. All right. Any other questions? Okay, very cool. Okay, so let's talk a little bit about Lie brackets and something called controllability. All right. So this section, we're going to introduce a couple of, kind of nifty mathematical tools. You might not have seen them before, but we'll try and just sort of break it down in more of an intuitive way. And then, yeah, we'll see how we go. All right. Okay. So our main question in this section, right, is we just came up with this nice representation of our system, right? Q dot equals U1, G1 of Q plus all the way through UM, GM of Q. All right. And now what we want to know is, can we move Q to any desired state Q desired while satisfying our constraint? Okay. So this is a really important question for us in robotics, right? Like if I'm moving my turtlebot around, I want to actually know, before I plan on going over there, is that a place that I can actually reach, right? Like, will I be able to drive out the door if I want to? That's a kind of important question as I'm trying to figure out what my robot can and can't do, all right? So this is very closely tied to this idea of controllability. Okay, and we'll define that a little bit more formally in just a moment, all right? Okay. So before we get started on the more mathematical side of this question, do we have just any like conceptual questions about the setup for like why this is something we're interested in? Okay. Okay, cool. All right. So something that we notice up here is that like all motions of Q dot are along these vector fields, right? Along these vector fields G1 of Q through GM of Q, right? So just remember that a vector field can like take in a vector and then return a vector as well, okay? So just because each of these G1 through GM are actually functions of Q, right? And they're returning these vectors in Rn, we say that these are actually vector fields that we're moving along, all right? So just from this expression up here, we know that all of our allowable motions are going to be some sort of motions along these vector fields in different directions, okay? So our question now, we could sort of rephrase this a little bit more mathematically and say that when we move along these vector fields, can we travel anywhere? Right? So we want to try and figure out if we can compose different motions along these vector fields to arrive at a location that we want, okay? If we could do that, then we'll have gotten to our final location while at the same time respecting this constraint that we need to be moving along these vector fields in the first place, okay? So there's this really nice tool we could use to figure that out called a Lie bracket. A Lie bracket. Okay. So here's an idea, all right? So let's just say that we have two different vector fields, all right? So suppose we have two vector fields, F and G. Okay, we want to figure out if we can travel anywhere by moving along F and G. Okay, so first off, let's say that, maybe my F vector field is sort of like pointing in a direction like that. Let's say that I'm starting over here, okay? So what I'm going to do is, starting from this point Q over here, I'm going to travel along the vector field F, okay, for epsilon seconds long, okay? And maybe that's going to land me up at this point over here, all right? And maybe at this point, my G vector field's sort of pointing in this direction, okay? So now what I'm going to do is I'm going to do a similar motion, all right? I'm going to travel for epsilon seconds along this other vector field G, okay? Travel for epsilon seconds along G, okay? And now I'm going to do something a little bit funny, but we'll see why we do this in just a moment. All right. So before we traveled epsilon seconds along F, now what I'm going to do is I'm going to try and go back the other way. Right. So now what I'm going to do is I'm going to travel backwards along F. Okay. Travel, say like minus epsilon along F. Okay. Then I'm going to do a similar kind of motion. And I'm going to travel like minus epsilon backwards along Z. Okay. Maybe this will take me like to some final location over here. All right, great. Along G. Okay. So what we saw in this case is that even though we performed this nice symmetric motion, right, like epsilon along F, then epsilon along G, minus epsilon along F, minus epsilon along G, because these vector fields are actually changing at every point in space, right, we might not end up at the same location that we started, okay? So might end up in a different location. And what this means is that by traveling along F and G, right, by these different amounts of time, we can actually get new directions of motion, right? So if we don't end up at that same point, we'll actually be able to travel to new locations by, doing these different combinations of F and G. So that's really good, right? So we can go to new locations if we end up at a new point. Okay. And this is really what we're looking for in control, right? We're trying to say that, okay, when we're moving along these vector fields G1 through Gm, can we go to all these different locations in space by, traveling along different combinations of these vector fields, okay? So we can formalize this idea of ending up in a new place with something called the Lie bracket. Okay. So if we have two vector fields, F and G, we can define their Lie bracket, which we call F comma G, these little brackets around it, okay? It's defined to be the following. It's going to be, it's going to be dg dq times f of q minus df dq times g of q, okay? So the really important property of this Lie bracket is that Lie bracket is 0 if we end up at the same place. Okay, so it sort of tells us about the difference between our starting location over here and where we end up. Okay, so we want to try and figure out like the difference between those two. We can sort of look at this Lie bracket and reason about whether we're going to end up at the same spot or not. Okay, all right, so our Lie bracket will be non-zero, is non-zero if we end up at a new location. Okay. So what this Lie bracket is really doing is it's saying like, okay, if we move along like compositions of motions along these vector fields, can we go to new positions in space? All right. So do we have any questions about what this Lie bracket is? What this idea is over here? So this is something that you could actually prove by doing like a little Taylor expansion along these vector fields, if that's something if you're interested in trying in your own time. But yeah, do we have any like conceptual questions about like why we're looking at this thing? Yeah,
Why is traverse for the backward parts? Why is the travel the negative time instead of travel along?
Yeah, so the reason that we're like going in this negative direction is really that, yeah, we are going like backwards along this vector field. But yeah, we just want to make sure that we're just traveling, like opposite to the direction of what that flow is. So that way we're sort of telling like if these two vector fields like undo each other or not. So if we say like, okay, we go along F, then G, then back along F, then back along G. If F and G undo each other, then we'll end up at the same spot, but otherwise they won't.
So that is the travel for negative delta along F is equal to the travel for epsilon along negative.
Yeah. Yeah, exactly. Yeah. All right. Any other questions? Yeah.
Can F also go to different points on every time step just like G did on the way back?
So not necessarily. It's going to be constrained by like what your like Q is over here. So if you think about these F and G's, like if you have like a differential equation, we call it like Q dot equals F of Q. we know that in general, the solution won't be able to, you know, like reach every point in space. It'll depend on our initial condition. It'll sort of constrain like where our Q travels as we go along.
But like, you know how on the way back, G just like went different location than like the way we went forward? Can also F on the way back, can they just do like different location?
Yeah. So in general, like when we're looking at a vector field, right? These could really like be pointing in arbitrary directions in space over here, right? So we could have like something like that. And maybe it will like spiral in towards the origin. So these arrows could really be pointing in like in any direction. So say if this is our F, for example, and we start like over here, right? We could always end up like spiraling in along the trajectories of F, something like that, okay? So they can actually be pointing in different directions at all points in space. Any other questions? How are we doing? Yeah. Cool.
For all Q,
Is it?
do you check it, do you have to check the brackets for all Qs or?
Yeah. So in general, if you're looking at this, you will have to check at each Q. So generally, like when you're defining controllability, you define it like at a point Q. Yeah. All right, awesome. Any other questions?
It will tell you, like then you define it as Q and then it tells you, okay, from this Q you can get to a different position. It doesn't tell you that you can get anywhere.
Right. Yeah, so there's a nice theorem about it. Yeah, we're getting there. We're getting there. Yeah. So yeah, so just try and keep this idea of like moving to arbitrary locations in the back of your mind. So this Lie bracket doesn't tell you about that just yet, but it's sort of going to help us try and figure that out. Yeah, I'm glad you brought that up. Yeah. All right, very cool. Okay, so there's another nice concept that sort of extends from this idea of a Lie bracket called a Lie algebra. All right, so what a Lie algebra is it is the span of vector fields G1 through Gm and their Lie brackets. Okay, so it sort of tells us, all right, like where can we go along G1 through Gm, and then what about along like G1 Lie bracket G2, like maybe we could have like G1 Lie bracket with G2, G3, like so on, things like that, okay? So it's saying along like all different combinations of, you know, these vector fields, all different like compositions and Lie brackets and that sort of thing, like where can we sort of go along these vector fields, okay? So it's just saying, all right, you know, along all these vector fields and along all their combinations, like what's the span of that sort of thing, okay? All right, so using this concept, we can come up with an idea of controllability, all right? So small time local controllability, all right? And I'm going to state this somewhat informally, just for the sake of, you know, not using too much notation. But what we essentially say is that if the Lie algebra of G1 through Gm has dimension n, right? It has the same dimension as our state vector, or excuse me, as the number of generalized coordinates that we have. It has dimension n, and we can control our inputs, what should we call it, U1 through UM arbitrarily. Then at a point Q, we can reach all points in a ball containing Q in finite time. Okay, so what it's saying is that, all right, if at a point Q, these vector fields, their Lie algebra has a dimension n, right? If the dimension of, you know, these different vector fields and then their, you know, different compositions has dimension n at this point Q, and we could sort of set our inputs a little bit arbitrarily at that location, then we can actually reach all points in the small region surrounding our system. Okay, so this is what is really important for, you know, these different ideas of holonomic and non-holonomic constraints and determining where we can actually go. So for our turtlebot, we can prove that our Lie algebra will have the correct dimension, in that case 3. So we'll sort of be able to drive it to any position and orientation in finite time in some nearby location. All right. So we're going to leave it off there for today. I'll upload all of the solutions to the questions. I know today was more of a conceptual kind of day, but yeah, I'll stick around afterwards if you guys have any questions about this. Yeah, what's up?
So is there like a connection between like